is hydrocracking. Hydrocracking is a catalytic chemical process used in petroleum refining to break down large, complex hydrocarbon molecules into smaller, more valuable products such as gasoline, diesel, and jet fuel. It involves the addition of hydrogen under high pressure and temperature, which helps to convert heavy oils and residues into lighter fractions. This process is essential because it helps meet the demand for cleaner fuels and optimize resource utilization. The hydrocracking unit typically consists of reactors filled with specialized catalysts that facilitate this chemical transformation efficiently. For this slide, I want to explain about three essential reaction mechanisms employed in the petroleum industry to enhance the properties of hydrocarbons. First, hydrogenation. Hydrogenation is the process of adding hydrogen to unsaturated hydrocarbons, which typically contain double or triple bonds. This reaction occurs in the presence of a catalyst, often a transition metal like nickel, palladium, or platinum. The significance of hydrogenation lies in its ability to convert less stable and saturated hydrocarbons into more stable saturated forms. For instance, the hydrogenation of pentane C5H10 can yield pentane C5H12. This process not only increases the stability of hydrocarbons but also improves their energy content, making them more suitable for fuel application. Number 2, cracking. Cracking is a pivotal process in petroleum refining that breaks down large, heavier hydrocarbons molecules into smaller, more valuable products such as gasoline and diesel. This can be achieved through cracking, which uses a catalyst to facilitate the reaction at lower temperatures. Example of thermal cracking is the conversion of hexadecane C16H isomerization and ring opening. Isomerization is have different physical and chemical properties. This process can enhance the octane number of fuels, improving combustion efficiency. An example includes converting N-hexane C6H14 into isomers. More desirable for fuel application. For instance, cyclohexane C6H14 through ring opening. This mechanism is particularly useful for maximizing the yield of high octane fuels from complex hydrocarbon structures.
Let's explore three key applications of hydrocracking product in real life and why they matter economically. First, we have diesel fuel, one of the main products of hydrocracking. Diesel is widely used in transportation such as trucks, buses, and trains. It's also essential in agriculture for powering tractors and harvesters, and even in power generation in some areas. Economically, diesel is in high demand around the world because of its high energy efficiency. Refining it through hydrocracking allows industry to convert heavier, low-value crude into profitable diesel. And since diesel fuel the freight and logistics sector, it plays a key role in supporting trade and supply chains globally. Next is jet fuel, produced by refining kerosene from the hydrocracking process. Jet fuel is critical for both commercial airlines and military aviation. From an economic standpoint, the aviation industry is crucial for global commerce, tourism, and national defense. Hydrocracking provides the clean-burning, high-performance fuel that modern jet engines require, meeting strict safety and environmental standards. Producing jet fuel domestically also reduces dependence on imports and improves a country's energy security. The third application is naphtha, a light hydrocarbon used as a feedstock in petrochemical production. It's a building block for making plastic, synthetic rubber, and fertilizer. Economically, this is extremely important because the petrochemical industry supports countless other industries from packaging and automotive to electronics. Hydrocracking helps meet growing demand for naphtha, especially in countries with strong chemical manufacturing sector. Converting low-value crude into high-demand chemicals adds significant economic value.
Sustainability and environmental impact focus on the hydrocracking process, breaking it down into 4 main categories. Category 1 is waste generation. Minimal solid waste those where the catalyst must be managed, such as disposed or regenerated. Wastewater includes ammonia, sulfides, and hydrocarbons. Byproducts like gases like methane, ethane, propane, and butanes are produced but typically recovered and reused as fuel or feedstock. Categories 2, emissions. Major emissions, CO2 and H2S formed during sulfur removal must be captured in closed units to prevent environmental release. Category 3, resource consumption. High energy consumption for hydrogen production and heating processes requires large volume of water and cooling utilities, strong dependence on non-renewable feedstocks such as vacuum, gas oil, and residue oil. Category 4, carbon footprint. Major CO2 emissions arise from hydrogen production, often fossil fuel-based, combustion in heaters, and use of fuels, especially in engine combustion. This slide outlines strategies to minimize the negative environmental effects of hydrocracking. First, use of green hydrogen. Replace steam methane reforming with electrolysis powered by renewable energy to reduce CO2 emissions from hydrogen production. Number 2, catalyst optimization. Use high-activity long-life catalysts to reduce regeneration frequency and waste. Recycle valuable metals such as nickel, molybdenum, and platinum from spent catalysts. Number 3, heat integration and energy recovery. Install heat exchangers to reuse process heat, increasing energy efficiency. Number 4, wastewater treatment. Apply advanced systems, for example, stripping, biological treatment to remove contaminants before discharge. Number 5, CO2 capture technologies. Use carbon capture and storage (CCS) or carbon utilization to lower plant emissions. Number 6, feedstocks. Diversification. Explore renewable feedstocks like bio-oils or use lubricants to reduce dependence on fossil-based inputs.
Assalamualaikum and hi, my name is Nurul Alia Balkis Muti Syed. My metric number is 33DPE24F1031. So now I will continue about process hydrocracking process for health, safety and legal consideration. For health and safety consideration, first about chemical exposure. Use high pressure hydrogen and various catalysts which can be hazardous Workers may be exposed to hazardous chemicals. So, the proper handling and storage protocols are essential to prevent leaks and exposure. Also, monitoring air quality and using appropriate PPE are essential. Number 2, high pressure hazard. Operates under high pressure and temperature, can requiring robust equipment design and maintenance to prevent accident. Number 3, noise exposure. Equipment can generate significant noise which may affect hearing. Due to implementing noise control measures and providing hearing protection is important. Number 4, water contamination. Wastewater discharges must be managed to prevent contamination of local water sources. So, it can pose health risks to nearby population. Number 5, emergency response plans. Facilities should have comprehensive emergency response plans to address potential accident. Number 6, air quality. Emissions from hydrocracking can affect local air quality. Compliance with air quality regulations helps protect community health. Number 7, stress and fatigue. The demanding nature of the work and shift pattern can contribute to stress. Ensuring adequate rest periods and mental health support is beneficial. Number 8, training and awareness. Ongoing training in safety protocols and health risks play a crucial role in maintaining a healthy workforce. Now, about legal consideration. Number 1, regulatory compliance. Facility must comply with regulation from agencies such as Environmental Protection Agency (EPA) and Occupational Safety and Health Administration (OSHA). Number 2, licensing and permits. Operating permits are often required and facilities must undergo inspection to ensure compliance with safety and environmental regulation. Number 3, reporting requirements. Incidents involving hazardous materials or emissions must be reported to regulatory bodies as per legal requirements. Number 4, process safety management (PSM). Following PSM guidelines help identifying, evaluating and controlling hazards associated with process involving highly hazardous chemicals. Number 5 is API standards. The American Petroleum Institute (API) provides standards that guide safe practice in hydrocracking and related processes. Number 6, fines and penalties. Non-compliance with regulations can result in significant fines and legal action impacting operational viability. Number 7, Resources Conservation and Recovery Act (RCRA). manage the disposal of hazardous waste generated from hydrocracking, ensuring that waste is handled and disposed of safely. Okay, now I will move on to awareness, current industry challenges and emerging trends. About current industry challenges, firstly, about feedstock variability. Refineries are processing heavier and more contaminated crude oils, which can foul catalysts faster and reduce efficiency. Foremost, catalyst deactivation. Catalysts degrade over time due to coke formation, metal deposition, and poisoning. For example, sulfur and nitrogen compounds. Frequent regeneration or replacement increases operational costs. However, about hydrogen supply and cost. Hydrocracking consumes large amounts of hydrogen, which is costly and energy intensive to produce. Fluctuating natural gas prices used in steam methane reforming that impact hydrogen economy. And number 4, energy consumption and carbon emission. High temperatures and pressure operations lead to significant GHG emission. GHG stands for greenhouse gases. Greenhouse gases include water vapor, carbon dioxide, methane, and nitrous oxide. Number 5, aging infrastructure. Many hydrocrackers are decades old and require upgrades or debottlenecking for modern performance and safety standards. Number 6, lastly, strict environmental regulations. Increasingly tight limits on sulfur content in fuel, for example, IMO 2020 marine fuel standards. Greater scrutiny on flaring, influence, and air quality. So now I will talk about emerging trends. First, advanced catalyst development. New bifunctional catalysts with higher activity, selectivity, and resistance to deactivation. Nanostructure and zeolite supported catalysts are gaining interest. Number 2, integration with renewable feedstock. Co-processing of bio-oils, of waste oils with petroleum feedstock in hydrocrackers for biohydrocracking helps meet renewable fuel mandates and carbon intensity targets. Next, hydrogen from green sources. Shift towards green hydrogen via electrolysis renewable electricity that to reduce carbon footprint. Number 4, digitalization and process optimization. Use of AI, machine learning, and real-time analytics for predictive maintenance, catalyst performing tracking and process control. Number 5, modular and small-scale units. Development of compact modular hydrocrackers for distributed or remote applications, especially in emerging markets. Lastly, circular economy and recycling. Exploration of hydrocracking for plastic waste and used lubricants, converting them back into fuels or feedstock. In conclusion, The hydrocracking process is a vital component of modern petroleum refineries, enabling the conversion of heavy oils fraction into high-value products like diesel and jet fuel. It offers flexibility, high yield, and improved fuel quality while meeting environmental standards. However, it requires strict adherence to safety, health, and environmental regulation due to its use of high pressures, temperatures, and hazardous chemicals. Overall, hydrocracking enhances refinery efficiency and product value while demanding robust operational controls. That's all from us about the hydrocracking process presentation. Thank you.